Good day, everyone. Today we will talk about one of the most important ideas in structures, load path. It sounds technical, but the idea is actually simple. Think of a building as a team. Every structural member has a job. The roof, slab, beam, column, foundation, and soil all work together so the structure can safely stand. In this video, we will explain how loads travel from the top of a structure down to the ground. After that, we will look at some structural wonders such as the Philippine Arena, suspension bridges, Burj Al Arab, retaining walls, and earthquake-resistant structures. So our main question is, when a building receives weight or force, where does that force go? That route is what we call the load path.
Structural load transfer is the movement of forces from one structural member to another until the load finally reaches the ground. For example, when rain falls on the roof receives that load when people walk on the floor. The floor receives their weight when furniture, equipment, walls, and finishes are added. Those also become loads. A structure does not simply hold the load in one place. Instead, it passes the load downward, step by step, until the load reaches the foundation and the soil. The usual load path in a building is as follows: roof, to beam or truss, to column, to foundation, and to soil. For floor levels, the usual path is floor slab, to beam, to column, to foundation, and then to soil. Think of it like a relay race. If one member fails to pass the load properly, the entire structure may become unsafe. There are different types of loads. The first is dead load. This is the permanent weight of the structure itself, such as the roof, walls, beams, columns, slabs, and finishes. The second is live load. These are movable loads such as people, furniture, vehicles, and equipment. The third is wind load, which pushes the entire structure from the side. The fourth is earthquake load, which shakes the structure horizontally and vertically. So, load transfer is not only about downward weight, it also includes sideward forces, especially during strong winds and earthquakes.
Let us start from the top, the roof. The roof receives different loads such as its own weight, rainwater, wind pressure, roofing materials, and sometimes equipment like air conditioning units or solar panels. From the roof, the load is transferred to trusses or beams. A truss is a structural frame often made of triangular shapes. A beam, on the other hand, is a horizontal structural member that carries loads across an opening. From the beam or truss, the load is transferred to the columns. Columns are vertical structural members. Their main job is to carry loads downwards. If beams are like arms holding the floor or roof, columns are like legs carrying the weight. Then, the columns transfer the load to the foundation. The foundation spreads the load over the ground so that the building will not sink, tilt, or collapse. Finally, the load reaches the soil. In simple terms, the roof says, "This is too heavy. Beam, please carry it." The beam says, "Column, I am passing this to you." The column says, "Foundation, take it from here." Then the foundation says, "Soil, let us spread this load safely." And this is how building stands properly.
Now, let's talk about load transfer per floor level. In a multi-story building, every floor has its own load. People walking, tables, chairs, partitions, cabinets, appliances, and floor finishes all create load. The first structural member that receives this load is the floor slab. The floor slab is a flat horizontal surface that people walk on. However, the slab does not carry everything by itself. It transfers the load to the beams, then the beams support the slab and transfer the load to the columns. Then the columns carry the load downward from floor to floor. For a typical floor, the load path is floor slab and then beam, load transfer to columns, downward to the foundation up until the soil. If the building has many floors, the columns collect loads from each levels. This means the lower columns usually carry more load than the upper columns because they support all the floors above them. Think of it like carrying a backpack. If there is only one book inside, it feels light. But as more books are added, the backpack becomes heavier. The lower columns are like the person carrying the entire backpack of the building. This is why structural design is very important. The size and the strength of the slabs, Beams, columns, and foundations depend on the amount of load they need to carry.
Let us quickly identify the main structural members and their functions. First, the roof collects loads from weather, roofing materials, and the equipment. The slab carries floor loads such as people, furniture, walls, and finishes. The beam supports the slab and transfers the load horizontally to the columns. The column carries loads vertically downward. The foundation receives the load from the columns and spreads it safely to the soil. The soil is the final support of the structure. So even if we usually admire the visible parts of a building, such as the facade, interior, or roof form, the invisible load path is what keeps everything stable. A building should not only look good, it must also have a clear and safe structural system.
Now, let us move to the structural wonders, starting with the Philippine Arena. The Philippine Arena is known for its large span dome structure and column-free interior. This means the inside space can hold a large number of people without many columns blocking the view. Its structural system uses a large steel space frame roof supported by concrete and steel elements. The general load path is roof to steel supports or space frame to concrete structure to foundation and to the ground. The loads are transferred to reinforced concrete support and finally down to the foundation. What makes this structure interesting is its large roof span. Usually, the larger the span, the harder it is to support. But through steel framing and a carefully designed load path, the arena can maintain a wide, open interior. For resistance, the structure uses reinforced concrete for stability and steel framing for flexibility. This helps the building respond better to lateral forces such as wind and earthquake movement. The main lesson from the Philippine Arena is large spaces need efficient load distribution.
Next is the suspension bridge. A suspension bridge is different from a typical building because it carries loads across a very long distance. Instead of using many columns under the bridge, it uses cables, suspenders, towers, and anchorage. The main components are deck, suspenders, main cables, towers, and anchorage. The load path is vehicles and then deck to suspenders and then main cable through the tower and then anchorage up till below the foundation. The vehicles create live loads on the bridge deck. The deck transfers the load to the vertical suspenders. Then the suspenders transfer the loads to the main cables. The main cables carry the load in tension. Then the towers carry compression forces down to the foundation, while the anchorage hold the cable forces at both ends. In simple words, the cable are being pulled, so they work in tension. The towers are being pushed downward, so they work in compression. That's why suspension bridges can span very long distance. The system spread and load efficiently instead of forcing one solid beam to carry everything. The main lesson from suspension bridges is cables are strong in tension, towers are strong in compression, and together they create a long span structure.
Now, let us look at the Burj Al Arab. The Burj Al Arab is famous for its sail-shaped form. However, aside from its iconic appearance, its structure is also designed to respond to strong wind and challenging ground conditions. Its main structural features include a reinforced concrete core, steel exoskeleton, steel trusses, and deep file foundations. Its load path can be explained as roof and floor loads to steel trusses and exoskeleton, to reinforced concrete core, to pile foundations, and to ground. The reinforced concrete core acts like the main stabilizing spine of the building. It carries vertical loads and helps resist lateral movements. The steel exoskeleton and trusses provide additional support, especially against the wind forces. Since the building has a curved sail-like form, its shape helps reduce direct wind pressure by allowing wind to move around the structure. The deep file foundation transfers the load down into stronger ground layers. The Burj Al Arab teaches us that the structure is not only about strength, it's also about the form, aerodynamics, stability, and foundation design.
Another important structure is the retaining wall. A retaining wall is used to hold back soil. Unlike a typical wall that mostly carries vertical loads, a retaining wall resists lateral earth pressure. Its main components are as follows: wall stem, base slab or footing, reinforcement bars, drainage system, and backfill soil. The load path is as also follows: soil pressure to wall stem, to base slab or footing, to ground. The soil pushes sideways against the wall. The wall stems resist the lateral force through bending strength. The base slabs help prevent sliding and overturning. Drainage is also very important. If water builds up behind the wall, it creates extra pressure. That is why retaining walls often have gravel and weep holes to allow water to drain. The main lesson from retaining wall is controlling water pressure is just as important as resisting soil pressure. Without proper drainage, even a strong wall can fail.
Finally, let's discuss earthquake-resistant structures. During an earthquake, the ground shakes. The structure experiences horizontal and vertical movement. This creates seismic forces. A good earthquake-resistant structure does not only try to be extremely rigid, it must also be able to absorb, distribute, and safely transfer movement. Common earthquake-resistant strategies include reinforced concrete walls, steel frames, bracing systems, shear walls, base isolation, and lastly, flexible connections. A load path during an earthquake is different because the force is lateral. The structure must transfer sideways forces from the floors into the vertical resisting system, then down to the foundation. A simple seismic load path is floor diaphragm to beam and frames, and then shear walls or bracing foundation to the ground. The main goal is not only to avoid damage, the most important goal is to protect life by preventing collapse. So in earthquake design, the structure must be strong, but it also must be flexible enough to move safely.
To summarize, load path is the route that forces follow through a structure until they reach the ground. For common buildings, loads usually travel from roof or slab, then to beam or truss, then to column, foundation, then down to the soil. For special structures, the load path changes depending on the design. The Philippine Arena uses a large span steel space frame. Suspension bridges use cables in tensions and tower in compressions. The Burj Al Arab uses a concrete core, steel exoskeleton, and deep foundations. Retaining walls resist lateral earth pressure. Earthquake-resistant structures transfer seismic forces through frames, bracing, shear walls, and foundations, but in the end, every structure has one mission: to safely collect, transfer, and resist loads. Because behind every strong building is a clear load path. Thank you for watching.